Today we're going to be talking a little about per title encoding and what comes after per title encoding. We're giving this talk from the perspective of having deployed a per title encoding solution out to production earlier this year, and some of the lessons learned and future directions that we're taking that work. I'm going to start off by going over a little bit about what per title encoding is. Then we're going to go through some of the challenges we've encountered. We're going to talk about our upcoming work working on better bitrate selection and finish with a few remarks on where we see the future of this technology going. But let's dive in with what is per title encoding. Well, per title encoding starts with a fundamental assertion that there is no one-size-fits-all approach to encoding your content, that each piece of content or title in your catalog needs to be treated differently if you want to be able to maximize quality. Now, this came out of, the name of this came out from a Netflix blog post that was published in December 2015, where they talked about there being the notion of a convex hull of quality, where if you followed the convex hull of bit rates and resolutions, you could maximize the quality that you were delivering to your users. But let's try and make that a little bit more real. Here I'm going to take two pieces of content, a fairly high complexity piece of content and a fairly low complexity piece of content. And I'm going to do a bunch of encodes. I'm going to pick a whole bunch of different widths. I'm going to pick different bit rates starting at 200 kilobits and moving up by 10% or 50 kilobits. And I'm going to use some pretty decent, fairly standard encoding settings. Then, at each of these encodes, I'm going to use Netflix's VMAF tool to figure out what the quality of that encode actually is. Here you can see what the surface looks like for high-quality content. You can see that down at lower bit rates, we're getting much lower qualities. You can see that as we increase bit rates, quality gets better. But you can also see that here, picked out in red is, given a specific bit rate, which width would actually maximize quality. You can see that that shifts up. Now look what happens with the lower complexity content. Here, the shape of the surface shifts dramatically. And also, that line going through here, picking out which encode would maximize quality for a given bit rate, also shifts. Plotting that in 2D, you can see that this is a representation of that convex hull, where we're following along, given a bit rate, what would be the width that would maximize our VMAF quality. So there are a couple of things we can do with this data. Obviously, the first one is what I just described. Given a bit rate, pick the width that will maximize quality by varying the resolution. Looking at this full space, though, we could also maintain a given a resolution, we could maintain a quality by varying the bit rate, kind of like doing a CRF-style encode. Or, given a quality, we could minimize our bit rate by varying resolutions. But for us, what we care about most is, given a bit rate, maximizing quality. And we built a really cool solution to actually deliver this out to our users. To explain that, I'm going to pass you to my colleague, Ben.
All right, so how did we build our per title solution? Or rather, how does anyone build a per title solution? Because if you do, you're going to run into three main obstacles: the cost, the speed, and the accuracy. Now, it seems to be like one of those situations in which you pull on one lever to improve it, the others get worse. So if you want something accurate, it's going to be slow and expensive. But what if there was a fourth lever, a magical lever, in which you pull it and all the other levers don't get worse? What if this lever was called something like machine learning? Well, how would you teach a machine to do per title? Or rather, how would you even teach a human to do per title? Because if you can't teach a human to do per title, it's going to be even more difficult, although not impossible, to teach a machine to do it. So I want you to imagine yourself as a little per title worker bee, okay? And as your job is to create convex hulls from videos. So how would you start? Well, you'd probably start just by watching the video. And pretty soon after the video starts, you start labeling the video under certain categories. Like, this is clearly an animation. It's a comedy. The main character is a horse. And then, as part of the training process, we show you what the convex hull for that looks like. You say, OK, and a few videos later, you watch another video. You say, all right, this one's an animation. It's comedy. The main character is a pig. Then we ask you to tell us the convex hull. And you're like, well, that's probably similar to the one with the horse. And that's probably going to be a pretty accurate similarity between the two. So pretty soon, you don't even really need to watch the video. You just need to see a few frames of the video to put labels behind it. Or you can have another bee watch the video, tell you the labels, and infer a convex hull just from the labels. So this is basically how we built our machine learning solution. At the top level, we have an inception graph, which is a deep learning image recognition graph that pulls visual information from the video, and in essence, watching the video just like a human would. And then we have a video classification model trained off of millions of YouTube videos using the YT8M database. And that creates labels for the video just like a human would as well. That gets passed to a convolutional LSTM, which outputs a sequence of 54 bit rate optimized pairs just like a human would. Although maybe not that last part. OK, so this gives us our convex hull. And if you haven't seen this before, the different colors curves are the resolutions and the VMAP performance of those resolutions. And the outer edge of those is the convex hull, right? Except we have a problem, because this is not what the convex hull looks like when we output it. This is what it looks like, in which we have a sense of what the VMAP should be, but we don't really know what it is. All we know is what resolution to use at certain bit rate ranges. So there's an additional step we have to take. And we take features from the video classification layer, as well as from the convolutional LSTM, and pass it through a feature engineering layer, which allows us to create a VMAP estimator. And from that, we can actually reconstruct a pretty accurate representation of the convex hull. Now, we have to start selecting bit rates. So how do we do that? Well, for the top rendition, you can just set a VMAP target as what you want, for what you want the highest quality to be. So at Mux, we go with VMAP 94 because that's almost indistinguishable from the reference. And then you find the lowest bit rate that hits VMAP 94. So that's your top rendition. Now, before choosing the other renditions, though, there's some challenges that we discovered that need to be addressed.
So we deployed this model out to production. We have happy customers turning this feature on and getting better video quality. But then we also have a few unhappy customers turning this feature on and giving us feedback. And that led us to do some investigations and more research and come up with a few places where we hadn't really addressed some of the core challenges. Now, the first of those is that your quality really depends on your viewing conditions. So what do I mean by viewing conditions? Well, people don't just watch video on one device. They watch it on TVs. They watch it on their phones. They watch it on their laptops. Imagine an example. You're trying to deliver content that looks great as it scrolls by in a news feed to catch someone's eye. Perhaps it autoplays. Then there's a button there that you can click to make it go full screen. You have now delivered two different viewing conditions to your users at different resolutions. Now let's imagine that one of those at full screen is watching at 1080p and another is watching at 540p. If we go back to my previous Surface example doing all of the encodes, what we can actually do is change our VMAP to not look at a score based on 1080p, but instead look at it based on a score at 540p. And here I can pick out, again, that same route where quality would be maximized given the resolution width combo. But then if we compare it to the previous 1080p, we now have this scenario. We have two curves that no longer agree with each other. This is kind of a fundamental problem when trying to use per title optimization. And there are essentially only two solutions you can do. The first, here's a chart breaking down how at each bit rate, the best 540p and the best 1080p rarely agree. So the practical solutions you can use are, first, you need to understand how people are enjoying your content out in the wild. How are they watching it? At which bit rates? On which devices? You can then use this optimization, if you want to create optimal encoding ladders for each of those viewing experiences. That's the way you can optimize quality. Then, as people shift between, say, the 540p and the 1080p, you actually switch renditions and your entire ladder to a new ladder optimized for that viewing experience. However, in the real world, we often have to make compromises. And the compromises we often have to make are figuring out how to create manifests that, given the viewer distribution that we see, maximize overall viewer quality, not necessarily maximize it for one specific group of users. The next challenge we run into is that content actually has changing complexity. To try and explain this, I'm going to use a video stitched together from some Netflix test content that they donated to the ZIF collection. Here we have a video that starts with a fairly simple bar scene. This video doesn't exhibit very much motion, and it doesn't exhibit much complexity in the images. However, this then switches to a dance scene followed by a scene at a crosswalk with lots of people, lots of motion, lots of complexity. I ran at 1 megabit, several encodes at several different widths, segmented them, and then took a per segment VMAF. And take a look at what happens. In the initial stages, using a high resolution maximizes quality. However, if you continue to use those high resolutions after the content switches, those resolutions collapse their quality. In some certain cases, we get a small VMAF bump at the start by using even 1600 at 1 megabit, 1600 by, I think, 844. But that quality quickly collapses much lower than even a 768. Take a look. Here, I'm showing you the 1600 by 844 versus the 768 by 404. And you can see that on this frame, we've done a terrible job of encoding on the left. However, with the next scene, we would have done a much better job if we had delivered a higher resolution. So what do? Well, we just change the resolution of our stream mid-flight. Basically, we give up. We say that we no longer advertise a valid HLS stream. We advertise a 1 megabit stream and lie about the resolution. Then, with each of the segments we deliver, we optimize just that segment to look as best as it can. This is kind of wacky, but it totally works. You can deliver one of these streams to an iOS device, to Safari, to QuickTime. Why do I care about the Apple devices? And it also will work in Chrome and in Friends. This is really cool as well because it answers the next big question we got, which was, how do I use per title encoding in a live environment? With a live environment, you have a challenge. You don't know what the content type is going to be until you see it. So instead, you could solve this by a brute force approach. Run multiple encodes, run a quality metric like PSNR, SSIM, or VMAF on every single segment you produce, and pick the best one. Or you can use our approach, which is to have a machine learning model that's super fast. We can feed it a few frames of each segment, get a prediction as to what's going to maximize the quality of the current segment, and use that as our encode. These streams are wacky if you come from a traditional background because they are constantly varying resolutions. However, what it avoids is that collapse when you have picked the wrong resolution and you have a high complexity scene without sacrificing the quality boosts you can get in your lower complexity scenes. The next challenge we have is how to choose our bit rates. So that, I'm going to hand you over to Ben.
Thanks. All right, so heard about some of the challenges and some of the solutions. So let's say we've implemented all the solutions, and now we're back to finding our bit rates. So we talked about how to choose top rendition, and we could probably also choose lowest rendition, choosing something like 250 or 300 kilobits for every video. So how do we choose what's in between? Well, we decided to go with a reinforcement learning approach to doing so. The same type of AI that can beat you at Go, drive your car, and make robots that will definitely not murder you. And so we built it and turned it on and said, OK, select our bit rates. Great. All right. Now, you're probably thinking one of two things right now. You're thinking, look, I'm no data scientist, but that seems like overkill. Or you're thinking, look, I am a data scientist, and that seems like overkill. And those are two very compelling arguments. So let's put aside reinforcement learning for the moment and see if we can't come up with another way of solving this problem. So one of the things we can do is just divide up the sections equally, right? And this is OK. This is serviceable. It's like the PT Cruiser of bitrate selection, OK? And like with a PT Cruiser, it'll get you where you want to go. But at some point, you're going to ask yourself, can I do better? And the answer to both those questions is yes. So what are some problems with dividing it up equally like this? Well, for one, your VMAF jumps in between renditions are going to be equal. So that's going to lead to kind of quality smoothness issues. So you could shift the renditions so VMAF jumps are more equal. But what if you have more data? If you have some sort of data product that gave you a sense of what the bandwidth distributions are for your viewers. And so here we can see that in between renditions, certain number, the viewers in between will pick the lower rendition as their quality. So maybe we can put in an additional rendition where it looks like a lot of our viewers are currently sitting. And that means only half of them would shift down, and the other half would shift to a higher rendition, and they would see a bit of a VMAF gain. And so cool, that was that looks pretty good. And this might work if you have millions or thousands of viewers for this video, but what if you have 100 or 10 or 1? Then you're starting to question whether or not it's worth it to add an additional rendition. And to answer that question, you have to figure out what the cost of rendition is versus the value of additional quality gains for viewers. And it's not just quality that you have to care about, because renditions also impact other QE metrics like rebuffering and startup time. So now you're starting to come up with this equation in which you're trying to balance the cost of renditions with QE metrics, and not just QE metrics, but QE metrics for every viewer. So the number of viewers matter. You probably want to have some sort of scaling factor as part of that equation as well, because viewers' value doesn't grow linearly. And so while you're juggling that, there's other factors that you have to consider as well. Like with your bandwidth distribution, it's not necessarily the same bandwidth distribution for every single video. You could have different viewer populations with very different bandwidth distributions, and you have to take that into account as well. So we're left with this state in which we have a value or reward function and complex environment, and suddenly that AI is looking much more appealing. So that's what we decided to go with. We built a reinforcement learning solution based off of 2 frameworks that we're testing, A3C and Paula. And I won't go into the specifics of how really they work, but they're both policy gradient reinforcement learning models that work on an actor-critic algorithm. And so what that means for bitrate selection is we start off with an actor and a video simulation environment that sort of generates fake viewers and measures the QE results from those viewers. And so we pass the actor a video and a state. And the state could be like the bandwidth distribution or specific properties of that video. And the actor has a neural network that it uses to choose the bit rates. And this is called the policy of the actor. And it uses that to select bit rates that passes through the environment and gets back a new state, which is sort of the QE results of that action, and uses that to calculate the reward. And it does that a few times until it goes to a critic model, which is an identical model, except instead of the end of the model, there's not an action vector, there's what's called a target function that is used to calculate something called advantage. And advantage grades the policy and essentially tells the actor which policy is better than other policies. So the first policies are not going to be very good because they're just essentially randomized. It doesn't really know where to start. But as it goes back and decides to explore more policies, eventually it'll probably start finding improvements. And it'll go back to the critic, and the critic will weight better policies, and it'll continue exploring down those paths. And you do this a few million more times, and eventually you get an award-winning performance. And so how does this look in real life? Well, last week, this is sort of the results from a simulated test. The orange line is our actor-critic model. The blue line is the PT Cruiser of bitrate selection, in which it's just like a fixed ladder. We use the Apple recommended ladder. And you can see that it starts off worse than the fixed ladder because it's essentially just picking nonsense in the beginning. And then it starts to improve on the policy, and there's high variability here. But it does exceed the performance, and even though sometimes it dips below at certain points, for the vast majority of the time, it outperforms it. Now, some simulations, this is all simulated data, so we need to test this on real data in the future. But this is really exciting for us, because what this means is it leads to this virtuous cycle in which we are using data from customers to learn about their viewing behaviors, about their viewing conditions, and improving the video for them, which attracts more viewers, more data, and the cycle continues. Now, we're really excited to be walking down this path. There's still a lot of work we need to do. But where does that leave us now?
So we, as I said, we have this out in production. And one of the things that you might have noticed we didn't talk about at all right now was codecs. That's because the work we're doing, and one of the things we're really excited about, is that a lot of this is codec neutral. You're going to need to use these same techniques if you want to improve quality, whether it's HEVC, VP9. And looking to the future with AV1, what we're very excited about is that AV1 actually has built-in support for this notion of per scene changing resolutions to maximize quality. And they even have rad new tools like super resolution that do cool upscaling based on custom learned weights in there, which I think is really, really exciting.
So at the end of this, you might be tempted to think that we're just talking about one more type of automation or another type of optimization, and that's partially true. But this is also a reflection of how we want to think about video. To not exist as worker bees directly optimizing video, but rather as the human beings creating machine learning models that improve the videos for us. And in doing so, we push back and expand the edges of our ability to build better video.